We should never make a presentation of full belly. Okay, so I don't present myself. It's just an occasion to speak about multiple point geostatistics. Some of you know what it is. Some of you have used it already. And most people I use it a lot. I developed a lot of things, and people in my group who developed it, they're gone now, former PhD students and postdocs, like Fabio, for example, but this is up there. So it's good to give this knowledge here so people know a bit about it. So, hey, hi Daniela. So the idea is that in geosciences, we deal with lots of data. So we do machine learning, we do this sort of things. But one version of machine learning that is simpler is geostatistics. So why do we use this type of methods? What's the general context? Is that we deal with lots of data, and this data have lots of variabilities in all fields of geoscience, not only atmospheric science. And it's very rare that we have complete data. We have models to generate data that are everywhere, but if we deal with real data, they're either only in some locations, or even if it's a time series, there are always gaps. You hardly ever see a time series of an instrument that just records for 100 years without a failure or something. And even if you have the best sophisticated method, remote sensing, you have gaps in your data. It always happens. Or you have a resolution that you miss. You can always go high in resolution and so on. For example, you have point data that you have to interpolate in a grid. That's a very basic interpolation problem that you see everywhere. Or you have data that need downscaling, or you have gaps, temporal or speech. So geostatistics is the classical framework to address that. Just illustrate some of this data. Lot of data. So this is the DM of Europe. This is a remote sensing image. Or it could be a 3D, this is a 3D aquifer representation. So that's the hydraulic properties of a block of subsurface. And they vary, typically, this is a variable, hydraulic conductivity, that varies in orders of magnitude. You see the scale, 7 orders of magnitude in there. So it's a problem. What people traditionally do is what is illustrated there. They want to quantify the spatial variability of the data to interpolate it. So, because if you just interpolate your data with a classical, very standard way, like nearest neighbor, nearest distance, you have some interpolation that doesn't take account of the natural variability of the data. So first step would be to quantify how the stuff vary, do close nearby points present similar values or not. And one way to do this is to compute the variogram, a classical geostatistics. So we have here a bunch of dots. The color is represented to a value, it's completely synthetic. And then based on this, we compute the variogram. And for the variogram, you take every pair of your points, so you take all these points there, every pair of them, you look at the difference square of them essentially that's it. And for each of these points, you plot this, which is called the variogram cloud. So on this axis, you have the distance, the physical distance between 2 points. And on this axis, you have the square difference. And you hope that you see a structure in there. And typically here, you don't see any structure. In most cases, you wouldn't see any structure. So lots of points are very close together, a very similar value, although they're not close together. There are some here, some pairs of points that have small distance, but are still very different. And what people do with this, they adjust the function. So is this function, the purple one, if you want, is the model, variogram model, and they say this represents my data. I'm going to use that to have a model that represents the spatial variability. And of course, we see there that it doesn't work when the data is complex. When the data is simple, everything works. When in particular, what I argue is that when you have enough data, you can diagnose that your data don't fit these kind of models, and you have a problem. If you have few data, it always works because you can fit your data. So this is why we need more data when we need more models, different models when we have more data. So then after, when people have this, they use kriging, and this is the kind of interpolation you would have with this data based on kriging. So you have something smooth, and you don't know if things would vary locally, if there is small scale heterogeneity, you cannot find out. So an example of kriging applied to big data problem is this. We have a satellite image, Landsat 7. Some of you who followed my courses, they know Landsat 7 is the satellite with the problem because there are gaps in the scanner. So you have images like this. And for 15 years, that was the only satellite we had. So when we want to do long-term monitoring of the Earth's surface, we have data with gaps. It's not cool. So people use kriging to fill those gaps. And essentially, so you have an image, it's my mouse now, you have an image here with gaps. And when you krig the values inside, you get this blurry thing here, because kriging assumes some smoothness. Or at least when you fit this variogram, you don't have data everywhere, so you have to assume some kind of smoothness. And this, the cause of this is that you have a structure, a spatial structure that is very complicated. You see all those shapes, those things, and you want to fit another model with 2-3 parameters. You're never going to fit this complexity. So the model is correct if you want, but it doesn't represent the richness of the data. Okay, this is when the lines close. This is when people, see, for a long time, people have been not happy with those type of models. So they had this idea, let's come up with something else, which is multiple point geostatistics. And the name comes from the fact that we don't look at pairs of points, but at groups of points, okay, 3, 4, 5, or 8. So these are non-parametric models. How do you inform these models if they have all this complex, they're so complex, you need lots of data. And then data, you have to use analogs. So we call this training images. So it's an analog, another representation of the thing you try to simulate, where everything is known. So for example, you want to model a satellite image, you need another satellite image that informs the structure. And then you look at pair points, but patterns. So the first paper that worked on this was in 1993, and the implementation was very inefficient, it didn't work well, so it took 10 to 15 years to have something that really worked. So an example, I'm going to show it very simply. You have this training image that looks like this. It's actually a alluvial structure, it's a braided river, seen from above. And you want to interpolate those points, so black and white, based on this type of structure. Okay, so we have algorithms that do the goal. What you want is to generate things that honor all the points there. When you know it's black, when you know it's white. But at the same time, in between, you're going to interpolate something with this kind of structures. And then it has to be stochastic, of course, because you want to quantify the uncertainty. So in between, so you can generate as many as you want of these models. They will all be different. And in the end, you can do statistics on the ensemble, which is that this is just the probability of having a white at any position. How does it work? The essential part is pattern matching. This tells you everything. You take a pattern, so you see a group that could be more than 2 points, 3, 4, 80, and you're going to match them in your data. And you match them using a distance metric, which can be, for example, a sum of square differences here. So x is a value, is a position, x plus h is a position of a neighbor, because you have a lag h, and z is the variable we try to simulate. So it's basically you do a sum of square differences over your patterns. So it amounts to this: you take a pattern and you try to fit it in a place in your data, and you go on. And actually, most of the time we don't work with patterns, but pixel by pixel. Is that me? That's it. I think that's the TV. Yeah, we had that. We have to do these settings on there. Okay, and this thing I've been shown before. You can have one black and white image and try to generate other images that look like it. You can do it also multivariate. I'll try to show an example after. So you have several variables. It's like an RGB image, for example, or any multiple variables, and you do the pattern matching across your variables. Okay, how the algorithm works exactly, I'm going to show the most basic implementation of that, which was the one of 1993, so the very first one. So you have a training image that is this thing with sort of blobs. And what you can compute statistics, you know that the global proportions, I have 67% of blue and 34% of yellow in my pixels. Okay. Then I want to, this thing down there is my simulation grid. So here I want to generate values that reproduce the structure of my training image. So and I have two data here, which I call conditioning data. So two locations only where I know the value. So first thing, I put everything in grid. It's a migration step. Then I have to define a random path. So this method, this is something important, it's called sequential simulation. So you visit all the pixels in a random order, and you define an order which is random. Doesn't have to be random, but in general it's easier. And this is just from I have 50 pixels from 1 to 50. No, it's not 50, but yeah, I have 100 pixels, so it's from 1 to 100, whatever. So this is my this is my order, and now I'm going to attack the first pixel, which happened to be this one in red here. So I identify the closest neighbors. So in this case, the n closest here two. I have only two. Here I can define just all the neighbors. So I have these two neighbors. And what I have is called the data event or a data configuration. So I know that for this pixel, I have with this lag vector a yellow neighbor and then a blue at this distance. So then I can go in my training image and I apply this. So I can start here. And here I have one event where this is yellow, this is blue. So I'm going to count one. I have a CPDF here where we count the number of occurrences of this one when the pattern of these two pixels are matched. So here I find one, I find another one, continue scanning. Here I find one that is yellow with the same pattern here. So then I increase this yellow bar and I continue everywhere. And I identify all the occurrences where I find this pattern. And then I'm done. I scan everything. And for this event here, I can find out that the frequencies in the training image correspond to 81% blue, 19% yellow. What do I do with this? I have a little PDF with only two values, and I'm going to randomly draw one. And in this case, I happen to draw 0.19. I happen to draw yellow. It's less probable, but can still draw it. And I put it in there. And then I continue. And then the important thing is that the next pixel is now going to have three neighbors. So every time the value I sample randomly becomes considered like a datum. And continue like this. And this is why we can get some randomness that propagates until the whole image is filled. And then this is, if you do everything, so that's the whole animation, you will see that in this case, there's a lot of repetition in training image. There's no surprise you get a pattern that is very typical. Okay, then there's one, if you go a bit further with this, so this was the very first implementation, but it was very slow, it didn't work well. So there's an alternative here called the direct sampling. And it's another algorithm I'm presenting here. And it's based on an idea that is really old, 1948, by Shannon. Maybe you know Shannon information theory. So he made this nice article where he explained the information theory at the beginning. But then there was one tiny paragraph in the introduction where he was speaking about something completely different. It was really like an aside. And he did some funny tests to try to generate random text. And this is the extract from his book. And in 1948, he didn't have computers then, it was all by hand. And he had to generate series of text. So first he took tables of frequencies of letters in English. Okay. And he tried to generate text with that. And then he looked at different ways of generating text. And in the end, he looked at methods that were very similar to what I presented just before. You start with a pair. I'm going to show. Yeah. You started with pairs of letters. What's the frequency of finding an E followed by a T? In all possible combinations. And then very quickly, he found out this was not possible because without computers and tables of frequencies of letters, you know, they're limited at the time. So he came up with another idea. And I'm going to illustrate it with this. So I'm going to generate random text based on training text, which is this. It's a 250-page book of Flaubert. I just took it because at the time I had the free ebook. And I could do the same as what Shannon did at the time. So he looked at the frequencies of letters. So I could look based on just the first page of this book, what are the frequencies of letters? So we know in French the E is the most frequent letter. Do the histogram, and then I can generate text just based on that. So I just take a random ASCII character based on the frequency, and I get that. So If you know French, it doesn't mean anything. Then I can do like channels. So I look at degram probabilities. So for every pair of ASCII characters, so I have table 256 by 256, and I look at the probability of precision of each. So I first scan my whole book, and I populate the probabilities, and then I draw the first letter. So it's an A, what's the probability? Knowing that the A is first, what's the probability of the next letter? And then I continue. Then I get this, which is not much better. But then I have a computer, and I can go to order 4, and it looks already better, especially, for example, the frequency of spaces is sort of correct. So you have words that have the right average size. And then let's go higher, and I cannot because my table of probabilities is too big. Okay, I could do a sparse matrix, but it's too slow, it doesn't work. So the idea of Shannon, because Shannon had the same problem, what did he do? He did this, which is essentially not looking at probabilities at all, just taking a book, take any book that is represented in French language, you choose your first letter, or your first couple of letters, and you open a page at random in your book, and you start reading. And whenever you encounter your letter, you take the first one, the first occurrence, you take the first letter that follows the one you're looking for, and you start assembling it. And then for the next one, you open your book at a new page, and you scan first occurrence, you take it. Okay. And this thing, 1948, it was just renamed direct sampling, and that's an algorithm that I can illustrate further. So, for example, based on this training text there, I want to generate a piece of text down here. So I start having PA. So I take a random location in my text, this one, and I'm starting reading. Yeah, I read, and PA, I find it here. So next letter R, just the first occurrence I find PA, I put it there, here. Then now I'm looking for AR, and I go sequentially, and I read, and first occurrence of AR, then it's U, and I take that. And then I continue, and I get something. Okay, and you can see just by looking at this that it's more computationally efficient than scanning everything. Right? I just have to scan the little bit of text every time. So now I can do it with direct sampling, order 13, and have a text, and you can try to read it, and it looks like a randomly generated text. It doesn't tell a story, but it is sort of, you can make a good illusion. And I did that in Danish also once, to present with Danish people, and they were happy. So now how do we go back to really images and interpolation? So what I presented before with the braided river, want to generate an image based on a training image, want to generate a simulation here based on a training image. So we can do exactly the same. I want to know the value of this pixel here, knowing 3 neighbors. I have a training image, and I just go in my training image and I try to find match. So this one here doesn't match because this is not the right color here. I go somewhere else, it doesn't match. I go somewhere else, and this one matches. So I just take the value and I put it there. Simple. And then I iterate, I have random pass here, and I iterate until everything is filled. So you see that in the text case, I didn't have a random pass. I was going sequentially. But I could do it with a random pass, which is actually for time series, when we use MPS for time series, we have a random pass. So you condition the past to the future and the future to the past. You jump around in time. It works very well to represent large-scale fluctuations. Okay, so the good thing, one thing to mention is that every time we simulate a pixel here, we look at the neighbors, but if you do it, if you have 1 million pixels to simulate, the last pixel is going to have 999,999 neighbors, which is really a lot, and it's not a particle. So we define a fixed limited neighborhood, often defined as a fixed number of neighbors. So here I take always the 4 closest neighbors. So at the beginning I have these 4 neighbors, so I have a very big neighborhood. And then as my grid gets populated, the neighborhood gets smaller and smaller. And this generally works very well to represent multiple scales in an image. Because at the beginning, you decide the large structure, you generate big objects, and then they become smaller and smaller, and at the end, you do the fine details. So, okay, the basic algorithm works like this, that you scan your image for a match, a pattern match. And in practice, what I showed in the text example, for example, you're never going to find an exact match. If you have a continuous, a real variable, you're never going to find an exact match, so you have to decide a threshold. You have to decide a distance function and a threshold, and also a number of neighbors. These are the parameters. And this is just the idea that you can use for the categorical variable. You can use a Hamming distance, which is the number of matching categories. You can use a Euclidean distance. You can use any distance you want, basically, and we played a bit with that. And a result of this, if you apply then this algorithm to this is the result. You have a training image which is based on stones here. Just we call it the stone image. And this we want to generate something in this grid, and we have 50, I guess, conditioning points. So every time the color, the point, don't see it very well, but it's a value that we know. So we generate this based on that. And for example, both images have the same histogram. Then we can compute all kinds of statistics, but basically our eyes tell us that, okay, the properties are respected. Okay, now if you want to use this, there's a nice code that was actually developed by Mathieu Gravel, as some of you know, and the documentation was largely done by Pau, and with examples and everything. It works a bit slightly differently than what I showed, because it doesn't do the Shannon sampling, but instead it scans the whole training image with FFT libraries that are very efficient, and it turns out to be faster. And this particular code has a nice feature that you have a server. So you run a server, which I can run on my computer, on a remote computer, anyone I have, I just need the IP address. And then I have also another part that is the interface, which is what communicates with the code. So I can run it, the interface and the server on my computer, or I can have just the interface here and run on kernel the actual code. And they communicate. And the interfaces, they are in R, MATLAB, and Python. So I'm going to demonstrate quickly the MATLAB thing, but the same exists in Python, and the interfaces work, the examples in both languages. So just to go back, so this code is the QS, not the direct sampling, but the quick sampling, because of this difference in scanning the image. So it has only two parameters, this one. One is the number of neighbors that we use, the same as the one I showed before. Typically, it goes between 10 and 100. 100 is a lot, but say 10 and 50 max. And the other one is the number of candidates we take. So since it scans the whole training image, you end up having a number of best candidates, and then you're going to sample one of them. This is how it works. So you have to choose between 1 and 10 candidates you retain, then you're going to sample one of them. And you can even use a fraction. So if you use 1.5, you retain you retain either the best candidate or with a 50% chance the second best. So you can split the probabilities. Yeah. And also you can weight your neighborhood. So you have this neighborhood, and you can give different weights depending on the distance of the neighbor pixels. You can have uniform, Gaussian, but in general we don't need any kernel, so we have the same weight for all the neighbors. So small demonstration. It's always cool to do a live demonstration. So this is on my computer, but it's only local. I have this thing here. It's a little DOS window. It's the server running. So this runs in the C code in parallel. And all I have in MATLAB is compiled libraries that just run it and do the visualization and submit to the server. So I can do a first example, which is the one I showed here. So this is a training image. I'm going to execute it.
Was there a laptop here in the room?
No.
Non, j'étais assis à la table au fond. Voilà. Je vais faire la recherche. Merci.
Okay, I'm just going to. Okay, so if I run it in live, yeah, so it's running, and there I got a new image. We didn't see it change because I had the image before, but you see a new image appearing here that has all this, I'll do it again, that has all the same structure as my training image. And okay, another example is the same but conditional. Wait, this. So here, this is with, I'm going to undock it to see a bit better. Oops. So here I got my training image. Here you probably don't see, but these are the conditioning points. So these are points where I know the value. And this one is conditioned to 50 points. Now I can add conditioning. So these are randomly drawn conditioning. I just take 50 random values. I'm going to do it again with 500. Okay. Do you see a difference in the image? What do you see? It changed with the.
Can you show the before one again?
Sorry?
Can you show the before one again?
No, because but I do 5,000 data. I take 5,000 random data.
Your stones.
Sorry?
You got bigger.
Yeah, we'll see what happens with 5,000 now.
Then if you lower your threshold, you wouldn't even converge, right?
Yeah, well, why does it work? Why is it so bad? When I have 5,000 random data.
For example, matching, because you have too much to condition on.
Yeah, but what's wrong with my conditioning data? Because if I had matching conditioning data, it would work. Because I take random. My conditioning data, they're random. They're just taking random, so they have no spatial structure. So they're not compatible with my training image. So if I wanted to do it correctly, I would have to take another image of the same type of structure, like real data, or make one big simulation that doesn't have conditioning data, big one, and then take the conditioning data from this.
Would that change if you had a bigger training image or a bigger training sample size?
In this case, no, because if the conditioning that I took randomly, for example, if they're random, they will never have connected paths of black values. This image, I need to have connected paths of black values. They will never have, what's the chance when you take random value that the low values become connected? So then you will get like little pieces of black here, maybe my mouse, but you will never get something logical. So we have developed in the past tools to validate the compatibility in the given data set and a training image, because you can diagnose this, right? So going through my examples. So these are, you see that these are very small pieces of code that essentially the running of the code is just, yeah, you don't see it, but it's just one line.
Someone has a question.
Yeah.
Well, no, I'm wondering, so you had a threshold, right, on your distance, and if you didn't go below the threshold, so if you strict enough, it shouldn't converge, right?
No, if you don't find anything at all,
okay,
you will still take the best match you have. You know?
Oh, got it.
Because otherwise, what do you do?
Well, I expected to stop converging as you added the number of.
But it's not there. You can't speak of convergence because you just visit every pixel once and you simulate it, and that's it. It's not interactive. So it's not. It's like you scan your training image, and the first match you find that's under your threshold, you keep it. So in this case, here the algorithm is slightly different.
Okay, but what if you never get below your threshold because you have too many conditional points?
Then you take the less bad. You still keep in memory what is the distance, and you take the best of the whole thing. But in practice here with the QS, it's slightly different because you have this K value, the number of candidates. Then you have 10 candidates. So you scan the whole training image, rank everyone, all the pixels, and take one randomly among the 10 best. Which is, it's just, there's no better strategy, it's just computationally works better. But that's the idea, is that you take one of the best candidates possible, and the next time if you run again, you will take another one because it's a random sample. So this one, it takes like a minute to run, so I'm going to show you the results directly. That's a multivariate simulation. So here, my training image is not one image, but it's 3 variables, and they're quite different. So I can start with this one. It's So yeah, green and blue values. This one is a smooth field, so it's not categories, but you see that it's related to this. Where you have this part here, this feature is there. Actually, they all derive from a same order random field that is transformed in different ways. And this one is tiny connected strands, but that is also sort of correlated to these two. But if you put a scatter plot of these three variables together, 2 by 2, you will find nothing. It will be super poorly correlated. Okay. And this is one simulation of this that is multivariate. So you can see that we can generate random shapes here that respect the relationship between the three. Wherever you have some green, you have these fuzzy values here, and you have these tiny connected values here that are randomly generated. So this is to show the multivariate application. And oh yeah, there's a gap filling, which is interesting. I'm going to dock my figure again for that. So here I have an image, the same training image, and I have a gap inside. So here I don't have another training image. I just have this data that inform my structure quite well. So this, the part around is going to be the training, and I'm going to generate values inside. And then I can run it a few times, and you see the result here, only the center will change. So every time you have another thing. And this, yeah, this goes super fast because most of the data are known already. And every time is sort of, could be a possibility. So the same applies to gaps in time series, so we have examples of that.
And it's continuous, then there's no discontinuity between.
Do you see? Yeah, we could, here in this case, the training image is really small. So the amount of training data I have there is quite poor. So you can see that sometimes he has problem finding matches. But if every time you see, there, I don't really see these continuities. And if I do it again, yeah, there I don't see, sometimes it's better than others, but in general, it's quite all right. Another thing is that you can use multiple training images. So here I have, in this example, yeah, so this is really artificial, but I have two training images, one with horizontal lines, one with vertical lines. So the one with horizontal line, I do a simulation and it looks like horizontal lines, but slightly randomized. They're not perfect. Then I can do something where I give the two training images, one horizontal, one vertical. Do what you want with this. And you see that it does these kind of things. So you can just generate some arbitrary hybrid model. In this case, this is a bit extreme and weird, but you can do things that mix different structures. And you can also weight them and do all sorts of stuff. And the last one is a downscaling problem. So here also I computed it in advance. So we have two images here, and it's a aerial image of dunes. So can I, if I zoom, these are dunes in the desert. You can zoom here. Okay, you can see it's sort of dunes, and this is a lower resolution version of it. Yeah. So what I'm going to say, I'm going to have the problem with consider two variables, like I did before, but one of them is known. So I have a domain. I want to generate the high resolution, but I know only the coarse resolution. So one of them is entirely known everywhere, the coarse resolution. Fine resolution, I don't know it, but I have this as a training image. This pair here as a training image. So I have an example of the corresponding high and low resolution. And again, this is a small example, but here you have the coarse inputs, so that's all we have. This is the downscale version, and this is the true dunes that correspond to this guy here. So you see, it's not perfect, again, because we don't have an infinite amount of patterns in there, but you could, and this takes about a minute or less to compute, but you can really generate some shapes that that resembles dunes definitely more than the coarse resolution. Okay, I can go back to my slides. So there's some real examples, applications of this. So if we apply this algorithm to this problem of the Landsat, this is what we get. So this is the gap fit values. And if you go close, which you cannot do, you don't see where the gaps were. There's no way you can tell even if you zoom a lot, it really works well. And this is because in this case, the Landsat image, the training image is really big. But the gaps are relatively small, but the whole image, I have really a lot of possible patterns that I can match. Unlike these little examples I showed before, where the training base is small. Another example with downscaling here. So that's a satellite image of Botswana, somewhere in Botswana, in the desert, because we have this satellite image that we purchased from years. And I have two images at this location, one which is a world view with 1 meter resolution, which is expensive. But here I have, I mean, everywhere, I have the planet labs image, which we have for free at UNIL. So here I have only the world view, but on the whole domain, I have both images. So it's a downscaling problem, where I say I want to generate for this lower half of the image, the world view pixels that I would have to buy for a lot of money. So I do the same kind of algorithm where I'm going to scan everything, find a matching pattern on the low resolution, then borrow the high resolution, and just plonk it in and do it everywhere. And again, I guess we can do statistics, which we did, but you basically retrieve patterns, and at the same time, you correct the bias. You see this image here has a different color, so it's basically biased, very short. And then since you resample values of the upper part of the image, you're going to be in the right distribution, and you correct the bias. And if I just have the time, we did the same thing a long time ago on downscaling regional economic models. And this is where we collected atmospheric science group. So this was in southeastern Australia, where we had colleagues who ran a regional climate model for all birds in 1985 to 2006. And with 3 variables of this model, the temperature, surface temperature, soil moisture, and latent heat flux. And the good thing with the model is that they were at 2 resolutions, the 50 kil and the 10 kil resolution. So we had in this case a synchronous model. So I don't know exactly how they obtained it. I guess that one was downscaled from the other, basically. But we had a synchronous model for this whole period. So we could really use one as training for the other. So the rule of the game was to say from 1985 to 2006, we have our 50 kilometer model, but only for 2006, we have all the models for all the period, except for 2006, where we missed the 10 kilometer. Then we tried to predict this single year. So we have lots of training. We have like 20 years of training and 1 year of prediction. So that's an ideal situation. And then some results. So this is the course input data. So we did it seasonally. This is only the results for summer. And it was, this is the course temperature. This is the reference high resolution temperature. So you can see that between the course and the real one, there are biases. For example, here we have mountains. So you expect a lower temperature, but it's not really lower in the high resolution. You can see the effect of the orography. Here also you see there's a Murray-Darling basin, I think, and you have more moisture around there. And in the lowest resolution, you don't really see it. And in our models here, this is what we downscale. You can see this kind of effect. There you can see something appearing. You see some orographic effect there. And for the latent heat flux also, you see the effect of some different land cover down there. And yeah, and the important thing also is that you probably know better than me, but these variables, for example, this is the relationship between temperature and latent heat flux. They're not simple. It's not simple linear relationships. They follow, they are thresholds and so on. So what we compared is the scatter plot essentially of these variables in the training. So that's the upper row, and in what we generated. So we reproduce, since we resample basically, we reproduce this sort of complex shapes. So every time the pair of the scatter plot between 2 variables is sort of these threshold effects, or these like this one, they are reproduced. Okay, so some properties of okay, I don't need to say this. I said it. Basically, in conclusion, directly, MPS can be used to generate complex patterns. The only constraint is you have enough prior information. So you need data that is representative of what you want to do. So it's not always possible to apply it. If you have very few data, use a variogram, because then you can fit it and you don't know what is wrong because you cannot find out. So it's fine. Often it's difficult, many applications, it's difficult to find training images. Some applications are easier than others, like remote sensing, you have lots of data, climate models, you have lots of data. One thing I didn't put in this slide is that there is really a parallel between multiple point geostatistics and what is done in machine learning with generative models. So there's really a similarity, and I believe that in the end, they do the same thing, but they rather the same thing in different ways. For me, the main difference is the need for data. So often when you train a model, a neural network model, you need lots of data. So some people have used multiple point geostatistics to generate data to train neural networks sometimes. So you have a small training image, you make 1,000 of them, variations, you give this to a neural network. In general, I think the difference is computational. Where do you want to put your computation time? If you train a neural network, you put everything before. A lot of time to train a neural network, and then you have it, you're happy, and you go generate, it's very cheap to generate. Here, the training takes no time, you just generate. Generation is slower, but if you want just one model, find it worth it. If you want 1,000 models, okay, train a network. And in terms of results, what the quality of how satisfactory are your models, there has been comparison, a few, and there's no clear winner. Depends on the case. Sometimes MPS gives things that are better, sometimes neural net, depends how you parameterize things. And I believe in the end, the most important is what training data you have. Then any good algorithms that is well-tuned will do something good. Okay, that's it.
Yeah.
Hope I'm on time. Thanks.
Thank you for a really nice presentation for us. And any question you want to ask?
Yeah,
I have two questions. First, I'm a bit scared to ask. I can see that you create something that looks realistic. Is it true? I mean, from our eyes, we cannot see that there's something weird going on, so it seems to be okay. But can we really use it to?
Yeah. So yeah, there's a lot of things in this question. So first, it's not, we don't generate, they look real, but they're not real. It's random data. So we never generate one image. I'll show one image because that's easier, but we never generate single image and say, okay, that's it. We will generate an ensemble and tell you this ensemble should represent the spread of the spread that represents the uncertainty of what we did measure. So first, then the next question is how can it be quantified? And I didn't show this again, but we have lots of types of metrics to see how good it reproduces our data. And these are always statistical metrics. So very simply, is the distribution, the histogram of my data respected? So assuming that the data, if I have a few data, maybe the sampling is biased. So I went in the field and I took some data, and I only stayed next to the road because it's easier to have a sample data set. So then I don't want to reproduce my data. So I need to have another thing. But if I know my reference statistics, I can try to see how I reproduce them. It can be spatial statistics. We use some things called cumulants, which is like variograms, but with more than 2 points, but they have an analytical expression. So we have these kind of tools to try to quantify how well we reproduce a given structure. And then the whole thing is that you're never going to be spot on a datum, you always have a distribution around some unknown function.
Okay. The second is, or it's a question or an idea. So I think your climate science application was about thermodynamics, so latent heat flux and stuff. In dry dynamics, I think maybe an interesting example is the closure problem in atmospheric models, that you have to limit your resolution of the atmospheric dynamical core at some point. But the problem is, via the advection terms, the small scales feedback on the large things. So if you want to simulate your fluid, your climate, your atmosphere, you need to make some assumptions about what's happening in the small scales that you cannot resolve. And I was guessing or thinking about whether you could use something like this to do, and I think it's called backscatter methods. So you have an idea of what's happening and how that scatters back to the resolved scales. The question is whether you could use something like this. Instead of simulating the small scales, we can generate a downscale thing and then calculate the backscatter.
So you have no assurance that the physical constraints are going to be met.
Yeah.
Except if if you have enough training data that is sufficiently constrained. You might want then to think about, this distance in the matching. You can use any distance you want. So you might want to have a custom distance. So we use custom distance for this kind of applications to limit what values can be done. For example, we have a project with Niklas now, where it's about geophysics, and geophysics tells you the values of something under the ground, but it's the average of a certain area. You have two measurements, and you have a line in between, and you know the average in between this. So we can, in the process of designing a sort of selection of these candidates based on constraint over areas that have a certain average. So this is something like this, where you could downscale, but with the constraints. You don't want to do something just random. Or you could also do this stochastic, generate many downscale models, and then do a model selection based, you don't want to buy the constraint too much. Yeah.
Think about it, thanks.
Had a question?
I was just, one of the things that I was wondering is if you're making the comparison with generative networks, right? Would there be a case in which you would want to train a network that can essentially reproduce this? Like you have the generator, you have the discriminator, right? If you can train a generator for, if you're trying to build a specific space that can do essentially the same, like can fool a discriminator that these two things are equally realistic, would that be something valuable?
Yeah, people did that. People really did exactly with the same problem, the same images, even community, and they did that. And they can generate things that are fine. Often the problem is that if you have this amount of training data that I showed in there, just this stone image, is not enough. You cannot train a gun with that. So it's not going to be enough. So you have to somehow expand the data. So then what people have done is just using these methods to take the stone image, generate 1,000 stone images, give them to a gun, and then you can have good results. But that's a bit circular way of doing it. But yeah, if you have enough data, if you want to do exactly this kind of downscaling, and people do that also with guns and all that kind of models. Yeah, so it works. It just like I said, where do you want to put your computing time, before or during?
I have some questions.
Yeah.
Like, we can use the MPS model to downscaling, also do the weather generation. And what do you think is the most advanced or MPS model to do the downscaling? Like, yeah, compare other downscaling methods.
So you use the QS.
Yeah, I use the QS.
Which works quite well. So many of these algorithms, there's like, I could name at least 15. Many of them are focused on categorical variables. But this won't works for geology, categories, the type of rocks, wouldn't work for weather generated. I think GANs for downscaling, it could work well for weather generation even. Often the question with neural nets is the representation of uncertainty. So here, there's this idea that we know what we randomize. We draw random numbers, there's the path, there's the drawing of the value, and so on. So we sort of know if we generate many varialization, they're going to sort of span the space of uncertainty. With GANs, it's all based on one network that is trained by optimization. So you live in one subspace. Other methods that could work for weather generation, so there are several. There are some non-training image-based, some variogram-based methods that work very well. Because sometimes, yeah, so for example, Lionel did his PhD in that. So you can represent everything as random fields that are transformed in complicated ways. and you also get very realistic fits. And it has advantages because it's faster and the uncertainty is better defined. You have also patch-based methods that don't work by pixel but by block. And it's fast, but you often see the block when it's simulated. So yeah,
yeah, because I use this model to downscaling the rainfall, and I understand this model, so I think that this model is really good at to reproduce the spatial pattern of the rainfall field, because like it's has this advantage than other downscaling model. Yes. Another question is like for the parameter of the MPS model, we have two important parameters: neighborhood n and the k. And the other option we can choose is the corner. Yeah.
you asked about the kernel.
Yeah, I think its corner is important to reduce the noise, right?
So this is a debate I had, and that's ongoing between Mathieu and I. And people generally don't use the kernel, and I don't use the kernel. I did lots of tests back my PhD where try to weight the neighbors, and it makes very little difference, and you don't know how to adjust that. So I said just give the same importance to all neighbors, and apparently, and Mathieu tried to optimize the kernel to get marginally better results. So yeah, you have one more degree of freedom, so you can do more stuff. I'm not convinced. There may be cases where it's better, but in general, I never felt the need to use the kernel.
Yeah, because in my application, when I do the downscaling, I just set the k and n in the model, and when I downscale the precipitation, I get some case like when I downscale to the fine resolution, I get some events like they didn't get a very good resolution. Like some rainfall they go to very high, very high. So in some noise, I need to.
I'm not sure that's related to the kernel. I think that's more related in your specific case to the training image selection, because you have this complicated setting for each day. You have a subset of training images that would match your day. And it's more related to for some days you have, maybe you have the right training image. It might be more something like this.
You mean from the training image? Yeah.
But yeah, this is.
Thanks.
I have one philosophical question, because intuitively, I guess I just don't really get it. If you go back to your example of you having this black hole in your stones, right? From what I understand from your algorithm is that it randomly chooses where to start the gap filling. So it could start in the middle of the black square. Intuitively, I would think it makes more sense to start at a place where there's more neighbors, and that would be in the corners. So
why? So we tried both. This is also gap filling. In general, if you go for random, it works. In certain situations, when your data are really all grouped in one place and not in other, it might be better, some cases, to do what you say, to have a path that starts with the data, but in general not, because you create artifacts, you reduce artificially the uncertainty at some places. So what happens if you start, I'm justifying the random part, if you start, am I sharing my screen here?
You can share.
It is sharing. But
No,
that's not. Oh yeah, there.
It's
Okay. That's no, that's not my screen. Yeah.
I think so. It's yours.
Okay. Can you please put me full screen? No, you. Full screen. It is. Yeah. I'm not sure if I. Okay, no, that's not my screen. Well, that's the screenshot. Oh, it doesn't matter. If I start right in the middle here, my neighbors are going to be there. Yeah, and I'm going to go in there, and I'm probably going to find nothing, or maybe something that is not related. So I'm going to take a random value take a random value somewhere, basically pick in the distribution one value and put it there. So then I decide, for example, if I take a light value, I decide that it's going to be stored in the middle. But then the next pixel already has more layers. So it builds on that. So the first pixel is going to be seed, but this is random. Based on one value, it will condition everything. If this value is black or if it's white, first value will infer a lot. But this is how you create randomness, because the rest is built around and you have this important spatial coherence between everything.
No, I definitely understand that you create randomness. If I think about like a one-dimensional time series from like weather and climate, I know the temperature today, then there's a gap, and then I know the temperature in 2 days. Then for me, somehow the temporal neighbors are important because I have a whole time series, I sample some temperature from it, but I know my neighbors that are like 20 to 25 degrees, so the gap will probably not be minus 40 degrees, right?
You mean in degrees? Temperature?
Yeah, like the temperature time series.
Oh yeah, you know the range of values. Yeah, because you do have data. I mean, if you have a gap that is 1 year.
Exactly.
Then all you have is the seasonality. So then, okay, you want to use the seasonality as a core variable, then we do that because you don't want to mix the seasons. But then the first pixel that you're in the middle of an unknown year,
Yes.
it says summer, so I take a random summer value.
Right.
Yeah, that's it. And then I build on that.
Okay.
And if you
need some covariance.
if you do this thing that you said,
Yes.
that is starting from the known places, I will start as an onion peel, and when I arrive in the middle,
Yes.
I'm screwed. Yeah, it's the same. If it's just a line, you grow you close the gap, and in the middle you have an incoherence. So in the way you choose where you want your artifacts. You want them in one place or spread randomly everywhere, and then you don't see them.
Yeah. Okay. No, I really like the randomness and the ensemble. So I appreciate that.
Okay, I'm just, because there's a lot of interest, we've never had so many people, so this is a wonderful way to climate journal club, but it's a lot of people are gonna have to leave very soon. So I just wanted to make 2 brief announcements. First, let's thank Gregoire.